All right, so today's session I am going over converting between logarithms and exponents. Logarithms are tricky until you kind of get a handle on them. And then, once you understand how they work, they're not so bad. They really aren't. Then they actually come in handy a lot. So let's start here with sort of to kind of get you thinking is why logarithms exist. So let's say you have the following, you know that 5 to the first power is 5, and you know 5 squared is 25, but you want to know 5 to what power gives you 20. So this is your question here is 5 to what power equals 20, and you're trying to find x. Well, we know it's not 1 and it's not 2. All we know is that it's between 1 and 2 based off of what we know so far about algebra and everything that we can do. So we know x is between 1 and 2. And that's all we know. And we don't know the exact number. We don't know if it's 1.5. We really have no idea. And you may need to solve a problem like this if you're in fields of chemistry, engineering, like this kind of stuff actually pops up a lot. And so we need to come up with something that allows us to solve this problem, because right now with our tools, we do not know how to do this. So this brings us to the definition of a logarithm. So for x greater than 0, so you can only take the log of positive numbers, and let me make sure that I make a note there. So you can only take the log of positive numbers. And then we've got b is greater than 0, and b is the base on the exponent. So that matches with exponential rules. And b is not equal to 1, because 1 to any power just doesn't mean anything. So the equation y equals log base b of x is equivalent to x equal b to the y. So basically, we've taken an exponential equation, x equals b to the y, and we can rewrite it in another form where y is the exponent, and taking the log of this gives you the exponent. And so we call this the logarithm. So we would find the logarithm of over here in order to find what x is. We'd want to find what is our logarithm. So kind of moving back and forth here, we've got this formula x equals b to the y. So x equals b to the y is equivalent, this is the definition of the logarithm, of y equals log base b of x. So in our form, we basically have 20 equals 5 to the x, which means that we can rewrite this as x equals log base 5 of 20. And so now we have a way to calculate this, but we need to know what exactly is log base 5 of 20. You need to know how to actually calculate that out in order to get your answer for x. Now there are actual tables. Way back when this stuff was invented, they had tables to figure all of this out, where basically you'd go, okay, 5 to 1, 5 to 1.1, 5 to 1.2, and then you would create a table of values, and then you'd look it up on a table. Today, we have calculators that do this for us, so we don't need to go back to these giant books of just logarithm tables in order to figure out what this answer is. But this is what the logarithm is doing, is it's taking some exponential equation that you don't know the answer to. You're looking for an exponent, and by taking the logarithm, you can now find the exponent. So that's what this definition of a logarithm is doing, is basically rewriting this problem so that our answer is the logarithm of this value. And so basically, if you've got y equals log b of x, y is generally your exponent. that b needs to be raised to in order to get an answer of x. So here, our exponent was x, so we need to raise 5 to some power x in order to get an answer of 20. That's what this is saying. So this answer is called the logarithm. That's what we've defined it as. B is called the base, and then x is also called the argument. And so these are equivalent equations. Y equals log base b of x and b to the y equals x are the same. Sorry, I've got sinus infection, so I'll probably be coughing throughout this whole thing. They are the same relationship, just written in different forms. So they are equivalent, and you can convert from one form to the other depending on which is easier. So when the log is involved, we call it logarithmic form. Otherwise, it's called exponential form. But these are equivalent equations. So what exactly is a logarithm? Well, the logarithm is the inverse of an exponential. So we've talked about inverse functions where they undo each other. And other types of inverses would be like multiplication and division. Those undo each other. Addition and subtraction, those are inverses. So the logarithm is the inverse of the exponential. Sort of like a square root is the inverse of squaring something. It kind of, in a way, undoes that exponent of 2. So exponential has an exponent of x, the logarithm undoes that exponent of x. Logarithms are really nice to give you an idea of how big of a number because it's giving you the size based off an exponent. So if you think of like billion or million, million is 10 to the 6th. The logarithm would give you 6, which is just telling you how big the number is. So if something has like a logarithm of 9, that'd be 10 to the 9. It's bigger. So it gives you an idea of how big a number is without actually like seeing the whole number, which is great for really, really, really large numbers. Another example here is, let's say you have two things, you know, the log of one is 5 and the log of the other one is 3. Their difference between 5 and 3 is 2. So the bigger one, the one that's log 5, is considered 10 to the 2 or 100 times larger than log y. It's not 2 times larger, it's 100 times larger because these are exponents. So these are really helpful if you're dealing with really, really large numbers or really, really small numbers. Which happens a lot in chemistry and engineering. You actually tend to work with numbers that have like times scientific notation times 10 to like -9 or something like that. And logarithms just make them easier to work with because instead of working with the number expanded out with all the zeros, you just work with the exponent, which is a lot smaller. So the key thing you want to think here is that logarithms give you the exponent. So if you have something, you want to know what the exponent is, that's what the logarithm does. So it's really important to be able to use your calculator to find the logarithm, or if you're familiar with programming languages, you can also use the logarithm because these are things that you can't necessarily do in your head most of the time. So on a calculator, most scientific calculators have a log button. And so that is assumed to be base 10, which means that whatever exponent you're looking for is 10 to some power. So it's going to be 10 to the x, basically, is when you're looking for that exponent. Now, if you have a graphing calculator, there isn't a button for log. There's only a button that says ln, which stands for natural log. I believe it's actually coming from the French phrase for natural log, which actually puts it in the opposite order, logarithm natural or something like that. So I think that's why it's ln. But that would be equivalent to if you're trying to find the exponent on something that has a base of e. So it's e to some power, and you want to know what that exponent is. And so e is Euler's number. It's a number that goes on forever, just like pi. So we usually approximate it to 2.72 or 2.718. But those are, on a calculator, those are what those two buttons are doing. So we've got the log button and then the natural log button. And those have different bases for your exponential. Now, what's really important is in programming languages, that's not how it works. the log in programming languages is actually the natural log. So for example, in Python, if you use the log function, it defaults to the natural log unless you specify a different base. So the default for log is actually a base E, not base 10, which is the opposite of what happens on calculators. So that's just something to be very aware of if you are choosing to do some of this stuff with your, I know a lot of people know Python because they're in computer science or something. If you choose to use your Python math functions to do the logarithms, it does default to the natural log. And it's not just Python that does this. Basically, any programming language tends, even in like MATLAB, which is used a lot in engineering, any of the log is defaulting to a natural log. And the reason why it does that is because a lot of these programming languages are used in scientific situations or used in engineering, and the most common type of log you do in engineering is actually the natural log. So it just made sense to make the default be the natural log because that's what you use most of the time. But it's just important to know that difference, because if you're not aware of that, your numbers are going to be completely off. You're not going to be getting what you're expecting to get. So where logarithms are used, there's a lot of equations that are used in science that involve types of the size of something. So you've got sound intensity, which is about decibels, how loud something is. That actually has a logarithm in its equation. The magnitude of an earthquake is using a logarithm. So, you hear about these earthquakes that are like a 2.0 versus a 4.0. And these are not like, oh, a 4.0 is twice as bad as a 2.0. It's like these are base 10. So it's actually 10 to the fourth versus 10 to the second. It's 100 times better. 100 times bigger than, a 2.0. So that's another thing where logarithms are used. pH is another formula used in chemistry that uses logarithms. It's often used in graphs when you have to graph things that are really big numbers. Instead, you'll use a logarithmic scale so that instead of graphing like 1 million, 2 million, you'll be graphing like their exponents, which is going to be like 6 or 7 or something like that. So they're just much smaller, easier to graph. They're used for solving exponential equations. And in particular, you are going to be using logarithms in pre-calculus, in calculus, both 1 and 2, and in many, many ET courses. One for sure is ET 310. ET 310 is a very math-based engineering course where it's basically a math course, but it's applied to engineering. So even though it doesn't have the math prefix, it is essentially a math class, but it's specific to engineering applications. And so that shows that you have to use logarithms a lot in that class for sure. So if you're somebody that is going into engineering, that's just, you're going to be using these things. So it's really important. Okay, so let's actually get to the examples. And so we're going to write these in exponential form. And I'm going to start by writing the, again, the kind of formula that we have based off of the definition. So if you have y equals log base b to the x, this is the same as saying b to the y equals x. Those are equivalent. And so you can write that they're equivalent. It's basically an equal sign with an arrow on each side. That's showing that they are equivalent. So we're going to just write these in exponential form. So we have it in logarithmic form, and we need to rewrite it. So the way that I do it is I take the base. So here is 9. And then I take what it's equal to, because that's going to be my exponent. So I always do that first. So it's going to be 9 to the second power, and then it equals my number that is kind of inside the log, 81. So that's how I I always start with the base, the exponent, and then whatever's left over. And so you can see, oh, 9 squared is equal to 81. If you're trying to write an exponential form and it doesn't make sense, that means you messed up because it's supposed to be a true statement. So log base 9 of 81 equals 2. What this means is if you're taking the log of 81 and you know that the base of the exponent is 9, the exponent is going to be 2. It gives you the exponent. So underneath this, we have log base 8 of 1 equals 0. So I start with the base 8, and then what's equal to is the exponent. So 8 to the 0 is equal to 1. And that is a true statement. And so underneath this, I've got one with letters. So it's going to be the base, which is A, to the exponent C is equal to B. So you want to kind of see the pattern here so that you know how to rewrite these properly. Now on the right, we've got log, and there's no number written there. So if there's no number written as a subscript, a little number underneath the log, that means it's assumed to be base 10. So this is telling us we're going to be 10 to the negative 4 power, because that's what we have the log equal to, is the exponent. And that equals 1 over 10,000. So if there's no number, assume that it's 10. The next one we have here is the natural log of 1 equals 0. So natural log is always base E. So if you see ln, that's the letter L, lowercase l, and I usually do it in cursive so that it doesn't look like 1n. So that's how I write on my papers, so I don't get confused, but it's the letter L and the letter n, that's the natural log. That's going to be base E, so that's going to be E to the 0 power equals 1. And then we've got another one with variables, so it's going to be x to the n equals m. Sorry, the sinus infection is killing me right now. So if you see this and you see the pattern, you kind of see how you write these. You kind of get used to it, and you're like, oh, okay, this is how I write it. Are there any questions on these?
Actually, I realized I came in a little late. I was kind of wondering, you have on log subscript 8, 1 equals 0. If you have 8 to the 0 power, how does that equal 1?
Aha! That's an excellent question. So our rule is that anything to the 0 power is equal to 1. And the way that I like to think about it is, let's say we have 8 squared, so that's 64. 8 to the first is 8. So if you notice the pattern, to go from 64 to 8, you can divide that by 8. So if you follow the same pattern, you're dividing by 8. That means 8 to the 0 has to equal 1, because 8 divided by 8 is equal to 1. And this pattern even works for our negative exponents, where you're dividing by 8 again. And so that would give us 1 over 8. And the rule with negative exponents is that it's reciprocal. So following that pattern, that's how we get the rule that anything to a 0 exponent equals 1. And that's why we also have e to the 0 equal to 1. If the exponent is 0, it's always going to give you 1 out. Does that make sense?
Yeah, it makes perfect sense.
Cool. Any other questions? All right. So that's going from logarithmic form to exponential form. Now let's do the other way around. So I'll copy it again. We've got y equals log b of x gives us b to the y equals x. So whatever is underneath our exponent is always b. So I know that this is going to be log base 2 because the 2 is underneath the exponent. So this is the base, and then what after the equal sign goes with the log. So that's going to be 32. And then the number that I have left over, the exponent, is what the log is equal to. So if you're kind of looking at the pattern here, I took the first number I saw and then the last number, and I set those up first. And then whatever number I had in the middle became my equal to. It's actually the same way here. It's just now we're writing it with a log instead of an exponent. So with my second one, my base is 10. So I'm going to need a lot more room here. So I'm going to have the log base 10 of the number that's equal to. Write the proper number of zeros there. There's 9 zeros. And then the number that I haven't used is the exponent, which is 9. So the log is always equal to the exponent. So some people might write the exponent first and then do whatever's after that. But I try to write it in the same order that I write my other ones, just so that I have like the same kind of habit of picking the first thing I see, the last thing I see, and then whatever's in the middle is left over and is the equal to. That's how I do it. So that's my base. So I'm going to take these two numbers. It's going to be log base A of B. And this is a subscript, which means that it's below the log, as opposed to like an exponent. Actually, that B looks like an exponent. So it's not an exponent. So that B is not an exponent on an A. The log is attached to the A is attached to the log, not the B. The B is kind of separate. And then this equals 7. Now, if you're trying to write this like without, like if you're trying to, type it out or something, the way you would type it, and you could actually even use this on Alex, is to indicate that the number is below, you use an underscore. And then you'd put a space in between the A and the B to make sure they're separated. So that's how you would type this out if you're trying to type it. And like that underscore is a shortcut for subscripts in any kind of math language. So it works in Desmos as well, if you're trying to do like a log or something in Desmos. But that's how you would type it. You can do that in Alex. You can even, you're not going to have to type this in a discussion, so you don't have to worry about that. But that's in general what we do when we're trying to indicate a subscript. So it's set below, and in like Word, there's the exponent button in Word. There's also a subscript button in Word, and you use that button instead. And I actually, usually when I'm typing in Word, I actually do that instead of the math because the shortcuts are almost the same. So top right here. So my base is 1/2, so it's going to be the log 1/2 of 32 equals my exponent, which is -5. Here we've got E, so log E, or you could write the natural log of E, because that's the other E, equals 1. So that this is also natural log E equals 1. So you can see how I wrote my natural log with cursive just so it doesn't look confusing. Usually with a log, you can see it's a word, it's like, oh yeah, that's log. But if you see ln, it's kind of harder to see that that's part of, that's a thing together, not just one n. And then this last one here, so our base is m, because that's under the exponent, so it's log m, and that's equal to n, so that's my next number. And then that final thing is equal to the exponent, which is 3. Questions on any of these examples? Okay. So now I'm going to show you why we want to do this, to kind of show you how you can use this to solve equations, because just converting back from one to the other isn't really useful in itself. We're usually trying to solve a specific type of equation. And converting it to exponential form or vice versa can actually help you figure out what your missing number is. So I've got log base 2 of 16 equals x. So the first thing we want to do is rewrite it. So it's going to be 2 to the x equals 16. So we're saying 2 to what power? What is the exponent on 2 that will give us 16 out? So you probably don't know your powers of 2. Some people are really good with their powers of 2. But 2 to the 4th power is equal to 16. And I know this because 4 squared is 16, and then 4 is 2 squared. So 2 times 2, that means the exponent would be 4. So you can rewrite this, and you see, okay, if 16 is 2 to the 4th power, if the things underneath are the same, then the exponents have to be equal. So then x has to be 4 in order for these to be the same thing. This is actually called the one-to-one property. So next one here, underneath it, we've got the log of 10 million equals x. So log without a number as in subscript is going to be base 10. So this is going to be 10 to what power gives us 10 million. Now the trick with the powers of 10 is you count how many zeros you have, and that's the exponent. So we've got 7 zeros here. Oops, this is still x on the left. So 10 million is actually equal to 10 to the 7, because there's 7 zeros. So we put it in exponential form, and then we're rewriting that other number, and then you say, oh, okay, so this means that x has to be equal to 7. So this value of x that's in the log is basically telling you the exponent. That's what the log gives you the exponent that you're looking for here. It's giving you, that part. So on the right, we're going to rewrite it. So I've got this base of 6, and then it's going to be 2 to the x equals 6. Well, 6 to the 1st power equals 6, so x has to equal 1. And then we've got base 3 to the x equals 1/9. So this one, we have to sort of use our rules of exponents here. So 1/9 is 1 over 3 squared. And then we can use the fact that you do the reciprocal, and it gets a negative exponent. So 3 to the x is equal to 3 to the negative 2. So that's from our rules of exponents, that you take the reciprocal and then the exponent becomes negative. So this tells us that x has to equal negative 2. Are there any questions? I know normally I try to make this a little more interactive, but with only one person on, I don't want to call you out and make you actually try to solve these on your own. All right. Here's some more, because we can never have too much practice. So we've got on the top left, ln. So that's the natural log, which means it's base e. So this is going to be e to the x equals 1 over e to the 8. So if I rewrite or 1 over e to the 8, if I rewrite that, that becomes e to the negative 8, because that reciprocal gives me a negative exponent. And so my answer here is x equals negative 8. And it looks like I forgot to actually write my equal to here. But that's okay. I can just write it in. I forgot to type that in. So log, again, no number as a subscript, so that's going to be assumed to be base 10. So we're saying 10 to what power gives us 1 over 10,000. Now we actually saw this on a previous, when we're rewriting, this actually came up. But if you're, you want to solve this, so we've got 10 to the x equals. So first I write 10,000 as its exponent form. So I count how many zeros. There's 4 zeros, so that's going to be 1 over 10 to the 4. When you have that 1 over, you can take the reciprocal to get the negative exponent. So that'd be 10 to the x equals 10 to the negative 4. And this gives us x is equal to negative 4. So now top right, I have log base of 1/4. So this is going to be to the x power. This equals 16. So this one's actually a little trickier. So what we're going to do is take the reciprocal of 1/4, which gives us a negative exponent. So that's going to become 4 to the negative x instead of x. And 16 is equal to 4 squared. So this tells us that negative x is equal to 2, which then if you divide both sides by the negative, you get x is equal to negative 2. And then we have natural log e to the 10 equals x. So the natural log is base e, so this is going to be e to the x equals, and then what I'm taking the natural log of is e to the 10. So this one just is set up so that we know, okay, x has to equal 10. Are there any questions on these 4 examples? Okay, so these are actually my final 4 examples. You can see I like to get them to be more complicated. These are definitely looking more complicated, but these are the last 4 that I have. So I'm going to start with the top left. I've got 1/6 as the base. So it's going to have an x1 of x equals 1 over 36. So 36 is 6 squared. And we can actually rewrite this as 1/6 squared. So we can put that square outside on the whole exponent, or the whole fraction, not just on the 6, because 1 squared is equal to 1. So here, then you can see, okay, so x has to equal 2. Now the next fraction one here, I've got 3/2 to the x equals 9/4. So this is going to be sort of the same thing. 9 is 3 squared. 4 is 2 squared. So what this means is that 9/4 is 3 over 2 squared. Because both the top and the bottom were squared there. And so just like the one above, this one gives you x equals 2. Now I've got log of 0.0001 equals x. So if there's no subscript, it's 10. So 10 to some power equals 0.0001. So I need to rewrite 0.0001. And just like when it was like 10 million, you counted the zeros. You count the zeros here, and you have to include that 0 in front of the decimal, because if you don't, you're the wrong number. So when the zeros are in front of the number, it's a negative exponent. So I've got 4 zeros here, so this is going to be 10 to the negative 4. So then this means that x is equal to negative 4. And then last one here, we have log base 3. So 3 is the base. So that's going to be 3 to the x equals 5th root of 3. Now, the 5th root we can rewrite as an exponent. The radicals, it's always 1 over and then whatever that index is. So this is 3 to the x equals 3 to the 1/5. And so this tells us that x is equal to 1/5. Are there any questions on these four? Okay, so I'm going to just, before we finish, I'm going to bring up Desmos to show you how you can use the calculator here in Desmos. So we're not going to use the graphing calculator. We're actually going to go to Math Tools, and then you can use the scientific calculator here. And so if you look at the scientific calculator, there's no log or anything here. But if you click Func, we've got the natural log and the log. So this is where you can find those buttons. So if I took that decimal one, log, and then in parentheses here, I type in 0.0001, you can see that our answer is -4, which matches what we got here by rewriting as an exponent and then using some kind of logic and rewriting our numbers as powers in order to figure out what that was. But you can type it into here and then you can get your answer. And so like natural log, see, I had one with the natural log. Natural log of e to the 10. So in here, I need to find e. So actually there's this button right here, there's two e's. There's regular e and then there's e to the x. We want to have an exponent, so we'll use this one. And so natural log e to the 10 equals 10. And that matches here when we solve for x. We got x equals 10. Now you may be wondering, well, how do I enter these other ones with the fractions? I actually have not tried to do this before. So I wonder if it can do subscripts. No. Okay. So this particular calculator will not let you do anything other than base 10 or the natural log. So I would not be able to use the calculator to do something like this. Now there is a formula called the change of base formula that would let me do this. And then I could just use it on the calculator, but it's about the same amount of work as doing what we did by hand. But something that's a regular natural log or regular log, you can do these on your calculator. And the reason why these are able on the calculator is because those are the most common ones that you have to do. It's rare that you have to do something weird like this. So calculators usually default to either just a base 10 or a natural log. But in Desmos, both of those numbers are available, and so then you can use these in order to do that and get your answers. So I just wanted to make sure that people knew where that was. So that's under function here and defaults to main, and you don't see those. So you have to go over here to function. And then there's these extra buttons. And you can even see that it has E, and it gives you a decimal approximation if you needed to just find that number as well. So are there any questions?
I do just have one real quick question before this is over with. I came in right I think right at the end that you were explaining the difference between the natural logarithmic function and the
Yes.
regular logarithmic function. What is the difference between those?
So that is the base. So let me see which slide do I have that on. So if we go back to this definition of a logarithm, so the regular log assumes that this base, this b, is 10. Because most of our, we usually use 10 when we're counting, that's our normal base system. The natural log has the number e instead. And so that has a special name called the natural log. And so that is abbreviated ln, where that base there is e. So, so the ln of x is the same thing as taking log base e of x, where that base is just this special number. And it's called the natural logarithm, or usually e is sometimes called the natural constant, I think, because it actually shows up in nature more than base 10. So a lot of things in nature actually use this special number, kind of like how pi shows up in nature, or the golden ratio shows up in nature. We've got these special numbers that just pop up. And so that's why it has the name natural logarithm. But that's the difference, is just the base. And because 10 and e are the two most common ones, those have their own like buttons, basically.
Okay, so the only difference is whether it's log or ln, and log is just the base of 10, and ln is like Euler's number, I think you said earlier.
Yes, that's correct.
That's the only difference between the two.
That's the only difference. You can use them the same way that you would use anything. When you're solving, you usually decide, do I want to use log or natural log, based off of if your equation has 10 in it, then you'll use log. If your equation involves e, you'll use natural log. And actually, when you're solving logarithmic equations, more complicated than the ones we have right now, the ones that we did here, solving them, we rewrote them in order to solve. But there's a different way to solve where you can take the log on both sides of an equation, and you can do either one and get the same answer. It really doesn't matter which button you use. So when I have my graphing calculator, I always use natural log because that's the button I have. But I get the same answers if I used the log on a different calculator as when you're solving, because you're doing the same thing on both sides, so it doesn't matter which one is which. So, I mean, they're really used the same. The only difference is that base, and there are certain situations where you have to use one versus the other one, but that's about it. They operate the same. They kind of work the same.
All right, that sounds simple enough.
Yeah, it seems very foreign when you're learning these things, but once you do enough of them, you say, okay, it's not so bad. it's just we're learning a new thing you can do to equations. Like we learned you could square both sides, and then we learned you could take the square root of both sides, more than just adding and subtracting. Now you're learning that you can take the log of both sides. It's another thing we can do to equations to solve. So just another thing to add to the toolbox.